Okay, here we are going to talk about how we solve linear first order DEs. Now recall linear means linear in your dependent variable, usually y. So no y squareds, no y prime squareds, no e to the y's, no nonlinear functions of y. You can do whatever you want to your independent variable. You could have x to the 10th. That's fine. You can't have any powers or other functions of y or any of his derivatives. So the first thing we're always going to do with linear first order DEs is write them in this kind of standard form where you get y prime plus some function of x or t, whatever our independent variable is, times y equals some function over here of x or t, whatever our independent variable is. I'm using Paul's online notes here to record this video. So we're going to call this like our standard form for linear first order DEs. Y prime plus some function times y equals some function. And these do need to be continuous functions. Okay, now the idea here is we are going to go through some work to find what we call an integrating factor. And we'll get to how we get that integrating factor in a minute. But for now, let's just assume that one exists, that there is some function that satisfies this equation right here. Some function mu of t that if I multiply it by p of t here, that is the same as mu prime. Well, let's assume that guy exists. Then if we take this original DE and we multiply everything by mu, both sides, then this left side here is the product rule derivative of mu. Let me explain what I mean. So we know our assumption here is that mu prime is mu times p. We've multiplied both sides by mu. We have this as our equation right here. Let's look at this left-hand side here. That is mu times y prime. Okay, this is the key to linear DEs. Make sure you pay attention to this moment here. Mu and y are both functions of t. If I were to take the derivative of that product, I would have to use product rule. So I would get derivative of the first times the second. That's right there. Plus, leave the first alone, times the derivative of the second. That's right there. So this is what makes the integrating factor special. When we multiply both sides by the integrating factor, the left-hand side will always be the product rule derivative of the integrating factor times y. And that's how we're going to write it. We're always going to, I don't want to say factor, but we're always going to rewrite this left-hand side in this form. The derivative of mu times y every single time. Why do we do that? Because then if we integrate both sides with respect to t or x, whatever our variable is, this is a derivative. The antiderivative of the derivative, those just cancel out. And I get mu times y equals the antiderivative of mu times g. What was g? You're looking at that and going, wait a minute, what was g? G was whatever we started with on the other side. And now of course, we get a plus c on both sides when we do these antiderivatives, but we're going to absorb that all together. And you can look through all the details here if you want. Like we do have a general closed form solution here. We're not going to memorize this formula. We're going to go through the process every single time. We're going to get to here. We're going to do this antiderivative. We're going to divide by mu and be done. Okay, now how do we find this mu? How do we find the integrating factor? This was our defining characteristic right here. This is what we wanted to happen so that this step right here would be true. Well, if we divide both sides by mu here, we could say, well, then P of t must be mu prime divided by mu. I'm trying to solve for mu here. You may remember from Calc 1, this is a pretty easy integral to do. So what we're really doing here is integrating both sides dt. You will never ever have to do this again. I am showing you the derivation of how we get our integrating factor. This math that's happening right now is just theoretical work that happens in the background. We're not going to be doing this ever again. If I integrate both sides here and I do a substitution, that's just natural log of u. 1 over u times u prime. We get natural log of u equals the antiderivative of p of t. I get, of course, plus a constant. And then again, we're not going to ever be doing this again, but I want mu of t. So I raise both sides and make both sides powers of e. So mu of t is e raised to the antiderivative of p of t dt. And then we got a bunch of nonsense with all of our constants of integration. We can squish them all together. You can read through all these details if you want, but we are never going to be doing that. Here is our key. This is our formula. This is what we were trying to derive. This is how we calculate our integrating factor. Mu of t is e raised to the antiderivative of p of t dt. What was p of t? Way back up here, it's the guy multiplying y when we're in this standard form. Okay, so then our process is, this is what you want to know. We get our dE into our standard form, which is y prime plus p of t or x, whatever our variable is, times y equals some other function of t or x. We find our integrating factor. Our integrating factor, mu of t, is always e to the antiderivative of p of t dt, or that's p of t right there. We multiply both sides by whatever we get here. This is the hard part because we have to actually do this integral. Multiply everything by that. Then the left-hand side is always, every single time, going to be the product rule derivative of mu times y. Then we integrate both sides with respect to our proper variable, divide by mu at the end, and we're done. Let's look at some examples. You can read through that example if you want. There's one down here I want to do. Okay, so we start with this dE here. This is a linear dE. It's linear in y. It's first order. We only have the first derivative. We're not in standard form. I need the thing in front of y prime to just be a 1. So we divide through by t to make that a 1. So we get to this standard form. So here is my p of t. It will be 2 over t. And here's my g of t. That'd be t minus 1 plus 1 over t. Now, you may recall we said earlier that these functions need to be continuous. Well, they are continuous, except at 0. So whatever solution we get at the end won't be valid at 0. But on, say, the interval 0 to infinity with a parenthesis on 0, our solution will be valid. Okay, so we've got this in our standard form. Then the integrating factor is always e raised to the antiderivative of this guy, not with the y, just the stuff setting in front of the y. So e raised to the antiderivative of 2 over t dt. That antiderivative is just 2 times natural log absolute value of t. Okay, now all the magic happens right here. This is the most important part. You're looking at this question and you think that that 2 is kind of inconsequential. What if I change that to a 4 or a 7? That wouldn't really change the problem, would it? Yes, it would. That 2 is the most important feature in this entire DE. Anytime you have something of this form, a number over t or x, this same math is going to happen every time. I would like to cancel that e and that natural log, but I can't in this form. Every single time we have an integrating factor that looks like this, we're always going to play this game. We're going to take that 2 and bring it in as an exponent. That's just rules of logs. Remember, we can take a number outside and bring it in as an exponent. When we do that, now e raised to the natural log of junk is just junk. They're inverse functions. They cancel out. That wouldn't work if I had something sitting here. That's why I need to get that 2 inside. So the e and the ln cancel out, leaving just absolute value of t squared, but t squared is always positive, so that's just t squared. So that's my integrating factor. Now we're going to take this original dE and we're going to multiply everything by it. So Paul doesn't write out all the details here. He kind of skips some stuff. So I'm going to write this out. T squared y prime plus, now I'm multiplying this guy by t squared. That will be 2ty, because one of the t's canceled out. T squared over t, one of the t's canceled out. T cubed minus t squared plus t. So I did some of the algebra in my head, but I've multiplied everything by this integrating factor. Now, if I've done my work correctly, and you always have to check this left-hand side should be the product rule derivative. This should be, I'm going to write this out. The left-hand side should always equal the derivative of mu times y. Mu and y. Let's check it. Derivative of the first, because this, remember, both of these are functions of t. We have to use product rule. Derivative of t squared is 2t times leave the second alone, plus leave the first alone times derivative of the second. What's the derivative of y? Y prime. Then Paul skips the most important step here. This is a step that's required. You have to write this out. Once we get to here, we integrate both sides. With respect to, I'm going to write this a little differently, in fact. I'm going to write this as, instead of writing a prime, the derivative with respect to t of t squared y dt equals antiderivative t cubed minus t squared minus t dt. You will never, ever in your life write this symbol. You will never write an integral without also writing a differential to go with it. These two go together. This is a required step. This is the place where I'll take a point off if you leave off your dt or your dx here. So we integrate both sides with respect to our independent variable. Then the whole reason this works, the antiderivative of the derivative, those just cancel out, leaving just what's inside. Then on the right side, we have to actually do an integral. This is where linear DEs can go wrong. Sometimes you get something over here that we just don't know how to integrate. I could easily make up a problem where what we get over here, we're just stuck. We're like, I don't know how to do that. I don't know that antiderivative. But in this case, we do. It's a pretty easy antiderivative to do. This is the moment we're going to put in our plus c. Keep this in mind. At this moment, when you integrate both sides, that's where you put in a plus c. Never put a plus c into your integrating factor. Notice up here, we did not put any kind of plus c or k. Notice we did not put a plus c on both sides. We're absorbing all of our plus c's right here when we integrate both sides. And then you can check all the details here. We're going to divide, once we do that antiderivative, divide both sides by that t squared. Notice that if I did not put my plus c in yet, if I tried to wait until the end to put in the plus c, I would have gotten the wrong answer here. You can't do that. It is like you'll get the wrong answer if you don't put the plus c at this moment when you integrate both sides. Then divide everybody by t squared. And then this was an IVP. This is our general solution. So maybe we'll write that here. Here is our general solution. We're looking for a particular solution. So we were given an initial value. You can see that at the top. I'm not going to go through all the arithmetic here. Here's our solution. Paul doesn't point out here in his notes that this solution is not valid at 0 because our functions p and g were not defined at 0. So we've only graphed t greater than 0 here. Okay, you can read through these other examples. This document is attached to this video. I'm going to do another example real quick here. Okay, first we are in standard form. This looks like y prime plus some p of x, x is our variable here, times y, forgot my y there, equals some g of x. Some books will call this a q. You might see in some videos that I'll call this side over here q instead of g, because different books use different notation. But we're in this form, check. Then my integrating factor, mu of x, is e to the antiderivative of p of x dx. So that's e to the antiderivative of -3 over x dx. Don't forget to bring along that negative. I see a lot of mistakes happen there. You got to bring along that negative. Okay, so what's that going to be? E's just coming along for the ride here. The -3 I could pull out. I'll write out the details here. I just pulled the -3 outside this integral. That will be e to the -3 natural log of the absolute value of x. Technically plus c, but we're never going to put a plus c in here. We're absorbing all of our constants into one at the very end. And again, you can look through Paul's notes where he proves you can do that. Then here's the key. Every single time we get something that looks like this, we're going to bring this exponent inside. We're going to write this as e to the natural log of the absolute value of x to the -3. Now, I don't want to deal with these absolute values, so we're going to take what's called the positive branch. We're going to assume x is positive. So I don't have to deal with this absolute value, and we're going to do that quite often. Then this will be e to the ln of x to the -3. E to the ln of junk is just junk. That's x to the -3. Every single time we have a p of x that has this, our integrating factor is going to be x raised to this power. This is always going to happen. As long as that's x to the first. If I had like x squared here, x to the 10th in the bottom, we would get something different because we wouldn't get a log. Okay, now that we got our integrating factor, so let's circle that. We multiply everything left and right by the integrating factor. So that will be y prime times x to the negative 3 minus 3 over x, x to the negative 3. Don't forget to multiply the other side. I'm just writing out all the details here. Multiply both sides by the integrating factor. And then I'm going to clean this up a little bit. This negative 3 could come down. Oh, I lost my y. There's a y there. That negative 3 can come down and hang out with him. And over here, what do we get? Just x to the 4th. The fact that I got 4 in both places is pure coincidence. Don't expect that to always happen. Now, if I've done this correctly, then the left-hand side, that means the left-hand side, should be the product rule derivative of y times the integrating factor. Let's check. So that would be y times x to the negative 3 derivative. Let's check that. Derivative of the first, leave the second alone, plus, I keep leaving off this y there. Leave the first alone, derivative of the second. Derivative of x to the negative 3, the negative 3 would come down, drop down by 1. Yes, it is. So this is derivative of x to the negative 3 times y. This is derivative of y times x to the negative 3. You always have to check that. So we're going to write it that way. Every single time we're going to write the left-hand side as y times the integrating factor derivative. Then we integrate both sides. Every single time in your life you write an integral symbol, you better have a differential sitting here with the appropriate variable. In this case, dx. I have to write the dx on both sides. This is a place people lose a point on the first test every semester. Don't forget to write your dx. Then the antiderivative and the derivative cancel out, leaving just y times the integrating factor every time. On the right side, we just do that antiderivative, x to the 5th over 5 plus c. This is the moment when you put in your plus c. If you put it in at any other moment, the whole thing's going to be wrong. Okay, now I don't want y times that. I want y. So I need to get rid of this guy. So I'm going to multiply by x to the positive 3. That's the same as dividing by this guy. Multiply both sides by that, and we will get cx cubed. Notice that if I tried to just wait until the end and tack on a plus c at the very end, my solution would have been wrong. You have to put the plus c right there. Okay, we'll do a bunch more examples, but I hope that's enough for a start. That's a good place to stop.